Thank you very much. And thanks to the organizers, first of all, for organizing this awesome workshop, and thanks for the opportunity to give this talk. I will speak about Fell bundles, Dixmier-Douady theory, and higher twists. And I will start by speaking about something very classical, namely Dixmier-Douady theory. I should also say that this is based on joint work with Marius Dadarlat, and the second part is based on joint work with David Evans. Okay, so let's start with something very classical, namely bundles from a topological perspective. So when topologists hear the word bundle, this is kind of what they think about. So here's the Möbius band as a bundle over the circle, right? So this looks locally trivial, right? So locally looks like a product, but it's possibly, I mean, in this case, it's non-trivial globally. And there's a structure group that somehow mediates the transition. In this case, the group Z2 that flips the fibres, right? And why are topologists interested in these kind of bundles? Because there's a nice classification result for these bundles via homotopy theory, right? So whenever you have any topological group G, you can cook up a topological space that's usually denoted by BG and is called the classifying space of G. That comes together with what's called a principal G bundle over EG over BG. And then if you look at the set of isomorphism classes of fiber bundles with structure group G, they turn out to be in one-to-one correspondence with this set of homotopy classes of maps from your space X to the space BG. And this might look very abstract, but this is very helpful because in many cases you can determine the homotopy type of this classifying space and then say something about the isomorphism classes of bundles, right? So for example, if I want to look at Hermitian line bundles here, then the structure group is the group U1, the circle group, and then you work out that the classifying space has only one non-trivial homotopy group that sits in degree 2, and therefore homotopy classes of maps from your space to this space BU1 here will be in one-to-one correspondence with the second cohomology of the underlying space with integer coefficients. There is a question in the chat. Are there assumptions on G besides topological? No, I think this is very general. You just need a topological group. There are several different constructions for BG. Some of them only work if your group is well pointed, but others work in the more general case as well. Right, okay. So you have this homotopy classification. Now we operate algebras, so we can look now at locally trivial bundles of C-star algebras, right? So what is that? That's one of those locally trivial bundles. And the structure group is, of course, the group of automorphisms of your fiber C-star algebra B, right? And this is a topological group where I can equip this group here with the so-called point norm topology. And so classically, Dixmier and Douady, what they looked at were bundles of compact operators, for example. So here, whenever I write this boldface K, I mean compact operators on an infinite dimensional separable Hilbert space, right? So this is what I mean by that. And then the automorphisms of the compacts, it turns out that they are all inner, right? So they're given by conjugation by a unitary, and the unitaries in the center are just formed in the group U1, and that acts trivially if I conjugate. So I get the group that's usually denoted by PUH and called the projective unitary group. And since this is the quotient of U of H by U1, you can work out what the homotopy groups are of the classifying space here. And it turns out that since this group U of H, of which this is a quotient, is contractible, this only has one non-trivial homotopy group, and it sits in degree 3, and it is the integers there, and all the other homotopy groups are trivial. And these spaces, which just have one non-trivial homotopy group, are called Eilenberg-MacLane spaces in topology. And just as with the previous example where you have BU1 and you get H2, since this here sits in degree 3, you get third cohomology instead of second cohomology. And this is the result of Dixmier and Douady. If I take isomorphism classes of bundles of compacts over my space, then that's in bijection with, first of all, this, which turns out to be third cohomology, right? So of my underlying space. And this association of a degree 3 cohomology class to my bundle of compacts is called the Dixmier-Douady class. And this association is very nice. So first of all, note that this codomain here, that's a group. And of course, then this is also a group. But the group structure is something that is intrinsic here, right? So I can take two bundles of compact operators and just take their fiber-wise tensor product. And then I get another bundle of compact operators. And that gives me a monoid structure on this thing here. And if I take the Dixmier-Douady class, that is compatible with this monoid structure. So if I take the Dixmier-Douady class of the tensor product of the two bundles, it's the sum of the two Dixmier-Douady classes. And in this situation, you can even work out what the inverse element in this group here is. That corresponds to taking the opposite bundle. So you take your original bundle, you just reverse the multiplication. And that gives me the negative Dixmier-Douady class. So that's all very nice, but compact operators are also kind of a boring C-star algebra. So the question is, can we somehow generalize this to more interesting C-star algebras? And the first question you should ask is, why did this work in the first place, right? So why did this compact operators work so well here? So one thing that made this work is this monoid structure that you have on the left-hand side. And that's, of course, based on the fact that if I take the compacts and tensor them with the compacts, I get something that's isomorphic to the compacts again. And that should remind you of something. So we've seen them already in this workshop. They're the so-called strongly self-absorbing C-star algebras, which have a similar behavior, right? So you take a C-star algebra is called strongly self-absorbing. First of all, if you have an isomorphism from D to D tensor D, and this isomorphism behaves very nicely, namely it's asymptotically unitarily equivalent to the left tensor factor embedding. And I chose asymptotically unitarily equivalent here. We have seen this with approximate unitary equivalence in previous talks. For strongly self-absorbing C-star algebras, this does not really matter. I think this is due to a result by, I think, Winter. I'm not 100% sure. Okay, and then if you take one of those strongly self-absorbing C-star algebras, you might hope that for bundles with this C-star algebra in its fiber, you get something similar here. So you can play around a little with this, but you realize then that if you take the automorphism group of your strongly self-absorbing C-star algebra in this point norm topology, this turns out to be contractible, right? And that also means that the classifying space is contractible as well. So there are no interesting bundles if I just look at the strongly self-absorbing C-star algebra in its fiber. That might sound bad at first, but there's also something good that can be gained from this. And that's the following statement. If I look at the K0 group of my strongly self-absorbing C-star algebra, this turns out to be a ring. And the way this works is pretty simple. You just take two projections in matrix algebras over D, tensor them together, get something in a matrix algebra over D tensor D, and you use this isomorphism to pull it back to D. And this, of course, relies on the choice of this isomorphism here, but then it doesn't, right? Because the automorphism, so any two choices of isomorphisms here will differ by an automorphism, but that's a contractible choice, so that doesn't matter. So there's a canonical ring structure on this group here. And K1 of D is usually 0, at least if D satisfies the universal coefficient theorem. Okay, so what about the bundles? Well, instead of D, you can also, of course, consider D tensor K. And in fact, that works much better and has an interesting homotopy type. But to explain what this is related to, I need a bit of stable homotopy theory. So here's my one slide of stable homotopy theory. So let's go back and look at this from a bird's eye perspective and see what's going on. So let's go back to the compacts for a second and to the group PUH here. This turns out to be homotopy equivalent to this classifying space of Hermitian line bundles BU1 here. And this is this first line. So PUH or BU1 both classify Hermitian line bundles over my underlying topological space. And then what I do here to get to bundles of compact operators is I take the classifying space, right? This is what classifies bundles of compact operators, as we've seen. And this also works on the right-hand side. So you can take the space BU1 abstractly. So there's a reason, namely the reason is that U1 is an abelian group. And this allows you to perform this classifying space construction essentially infinitely many times. So this has infinitely many iterations of classifying spaces, infinitely many deloopings, as it's called in algebraic topology. And yeah, so this all makes sense, but how do you generalize this, right? So if you think about these Hermitian line bundles for a second, then what they are is they are units in the topological K-theory of your underlying space, right? Because if you take a line bundle and tensor it with its dual, then you get the trivial one-dimensional line bundle, right? So that's a unit in K-theory, but these are not all units, right? To get all the units, since K-theory is not about vector bundles, it's about formal differences of vector bundles, you would have to take virtual line bundles, right? So you would have to take formal differences of vector bundles that have virtual dimension plus or minus 1. And you can ask, is there a classifying space for these virtual line bundles? That if I look at homotopy classes of maps from X to this classifying space would give me all of this group, the whole group here, GL1 of K0X. And there is such a thing, and it's usually denoted by GL1 of KU. And the KU here stands for the K-theory spectrum. So in stable homotopy theory, K-theory is represented by a spectrum in the homotopy theoretic sense. And it's a commutative ring spectrum. So therefore, there is a space of units for such a ring spectrum. And since it's a commutative ring spectrum, this space here, so this is not an abelian group like here, but it's the next best thing in stable homotopy theory. It's what's called an infinite loop space. And for these infinite loop spaces, this procedure here still works. So you can still deloop your space infinitely many times. You can still take classifying spaces infinitely many times. So you can take the classifying space, in particular of this space here once, and you get BGL1 of KU. The drawback of this whole thing is that this is something that you usually get from some kind of infinite loop space machine. So which doesn't really tell you what this actually classifies, right? So there's a question mark here a priori, so you don't know what this does, right? But comparing this with the bundle of compacts that we had here, you might have an idea, right? And that's what Marius and I looked at. And here's our result. So first of all, if I have a strongly self-absorbing C-star algebra, I can associate to it a commutative ring spectrum in the sense of homotopy theory, which we denoted by KUD here. And this is like, this is representing topological K-theory with coefficients in the K0 group of D, essentially. And then if I look at this space BGL1 of KU for this spectrum KUD here, and take homotopy classes of maps from X to BGL1 of KU, I get that this is in bijection with bundles, isomorphism classes of bundles with this C-star algebra as its fiber, right? So the purely infinite version of the D that I started with. Tensor the compacts. And so if I just pick O infinity here, then I get back this space that I just explained on the previous slide, BGL1 of KU itself. If I pick here one of those infinite UHF algebras, then what happens in K-theory is that this is localized. So you get K-theory with some number inverted. So there's a spectrum that represents K-theory with an integer inverted. And that's what you get here. So if you've never seen stable homotopy theory in spectra before, here's the thing that you should take away from this slide. So first of all, this here, since I started with an infinite loop space, this here is a group. And therefore, this is also a group. And this is compatible with this tensor product, this fiber-wise tensor product. So the group structure is induced by fiber-wise tensor product. The other thing that you should take away from this is that the right-hand sides here, since these come from cohomology theories, I can compute them using the tools of algebraic topology, right? So I can use, for example, the Atiyah-Hirzebov spectral sequence to compute this group here or any of the others. The fact that I have a purely infinite, strongly self-absorbing C-star algebra here is not terribly important. So even if I don't pick a purely infinite, strongly self-absorbing C-star algebra here, this will be an infinite loop space. And therefore I get a group if I look at homotopy classes of maps from X into this. Okay, so this is all kind of nice. But of course, then the next question is, are there any interesting examples? Does this come up in nature, right? So where do I get somehow applications of this strange cohomology theory from? And there is a prominent case where this space here plays a role, and that is in twisted K-theory. And twisted K-theory has some relations to mathematical physics via a theorem of Fried, Hopkins, and Teleman. So and this is on this slide here. So what they proved is that if I have a simply connected compact, simply connected compact Lie group, and if I take the loop group, the free loop group on my group G, then I have an isomorphism between this thing here, which is called the Verlinde ring of the loop group at level M. So these are formal differences of isomorphism classes of projective, of positive energy representations of the loop group at a fixed level. So this denotes the level here. This is interesting. This crops up in several places in mathematical physics, in particular because if I look at this, the category of isomorphism, the category of positive energy representations of the loop group at a fixed level, this is also one of those examples of a modular tensor category, right? And on the left-hand side, I get, first of all, what's this? This is equivariant K-theory in degree given by the dimension of the group. And as my G space, I consider G itself, but it's equipped with the adjoint action by G, which leaves us with this final datum. So what's the tau? This is a twist of K-theory. So this is equivariant twisted K-theory. And to explain this further, so there is a version, there is a nice way to express this left-hand side here using operator algebras. And this works as follows. So if I have my level M here, I can cook up the G equivariant bundle of compact operators, Km over G. And then this left-hand side here is just the equivariant operator algebraic K-theory of the section algebra of this bundle. Right? And of course, now you can try to generalize this situation here. And this is also the connection with what I've spoken about before, because this is, of course, one of those bundles that's classified by third cohomology. And the more general case should come from exactly from this space, and therefore exactly from bundles of this type, right? Which have D tensor K in its fiber. So are there any interesting examples that we can cook up? We have an example, and this arises from Fell bundles. So here's my one slide explanation of what a Fell bundle is. You start with a topological groupoid, G, and then I will only explain what saturated Fell bundles are, and I only roughly explain that. So a saturated Fell bundle is given by an analytic version of a bundle, namely an upper semi-continuous Banach bundle, E, over my groupoid. And then the trick is that over composable arrows in your groupoid, you want to be able to multiply the elements in the fiber, right? So whenever I have G1 and G2 and two elements E1 and E2 sitting over them, if I can compose G1 and G2, I want to be able to multiply the two corresponding elements in the fiber of the Fell bundle. And Furthermore, this is the saturated part here. I want, if I take the linear span of these multiplications here and close it, I want this to be, so I want EG1 times EG2, and then the closure of that to be equal to EG1, G2. I also need an involution on this Fell bundle that covers the groupoid inversion, right? And then there's lots of axioms that these two structures need to satisfy, but roughly what they say is that the fibers over the units of the groupoid should be C-star algebras, and the fibers over in the general fibers should be Morita equivalences between the source and the target C-star algebra. So if I think about this, if I forget about the topology on this bundle for a second, and for example, if I would just take a discrete group here, what this would be a functor from the category given by that group to the category of C-star algebras and bimodules and intertwiners. And one caveat here, since I've talked a lot about locally trivial bundles, so these Fell bundles are based on Banach bundles. These do not need to be locally trivial. So this is a different kind of bundle. And whenever I have such a Fell bundle over this groupoid here, if I pick, I think I need to pick a Haas system on the groupoid, but then I can associate C-star algebras to such a Fell bundle, like a reduced C-star algebra and the universal maximal C-star algebra. So this is how you get from a C-star algebra, from a Fell bundle, an operator algebra. So in this joint work with David Evans, what we did is the following. So we have a construction that takes as an input, instead of the level here, instead of this integer, it takes as its input what we call an exponential functor f on the category of vector spaces. I will say on the next slide what this is. And what the output of our construction then is it gives us a groupoid that comes with a G action that covers and a map to the group that is equivariant with respect to the adjoint action here and this action on the groupoid. And we also get a G equivariant saturated Fell bundle over this groupoid, such that the fiber over the unit, fibers over the, if I restrict to the unit, then the bundle is trivial. And the fiber algebra that you get here is one of those infinite UHF algebras that is related to this exponential functor. Right, and then what we could prove is that if we take the C-star algebra associated to this bundle and stabilize it with the compacts, then it becomes the section algebra of a locally trivial bundle where the fiber is now D tensor K, right? So this is one of those bundles with fiber D tensor K that I discussed previously. And then I can define equivariant K theory of G with twist given by this Fell bundle, just to be the operator algebraic K theory of this C-star algebra that we have here, right? So tensoring with the compacts is not seen by K theory, so I can forget about that here. And so far, our construction only works over SUN, but I'm pretty confident that there are generalizations of this to other Lie groups as well, I should say that. Okay. So let me tell you a little bit about the input datum. So what are these exponential functors? So an exponential functor is just a monoidal functor from the category of finite dimensional complex inner product spaces to itself, where I pick the direct sum on the domain and the tensor product on the codomain, right? That's what the exponential function should do. It transforms sums into products. Right, so here's that spelled out. I have a triple consisting of my functor and two natural transformations. One that is a natural isomorphism between the sum of two f of v plus w and f of v tensor f of w. And I also have a unit here, right? And I want the obvious associativity and unitality diagrams to commute on the nose. Right, so that's kind of a strict functor from vector spaces with plus to vector spaces with tensor product. Okay, so what are examples of this? So you could take the full exterior algebra functor and take its mth exterior power, mth tensor power. So that's an example, right? Because the exterior algebra functor has this property of transforming sums into tensor products. I only need this exponential functor in our construction to be defined on this subgroupoid of finite dimension inner product spaces and unitary isomorphisms. And if I restrict to that, then I have another example here. I can take the determinant functor or mth tensor powers of the determinant functor, right? So lambda top is the top exterior power or determinant. So that also works if I restrict to this subcategory here. There's a slightly more exotic construction where I take a vector space and basically do this. So if this is like a mix between the exterior powers and the tensor powers. So this also turns out to be an exponential functor. Then I wanted to give one non-example, namely if I take the symmetric algebra. So this also has the property of transforming sums into tensor product, but it ends up in infinite dimensional vector space. So this doesn't work, right? I want to have something that ends up in finite dimensional complex vector spaces again. And there is a class of functors on vector spaces that was first analyzed, I think, by McDonald. And he called these polynomial functors. And among these functors, I can classify the exponential functors, which leads to the slightly awkward statement that I can classify the polynomial exponential functors. The classification is via involutive R matrices, and that's based on joint work with Gandalf-Lechner and Simon Wood here in Cardiff. Okay, so that's our input datum. So what does our actual construction do? So we have this exponential functor on this isomorphism groupoid. Here's the groupoid that this construction gives us. It's just given by pairs of, so here's an element in the group, and these two are just numbers on the circle that are not equal to 1 and are also not eigenvalues of this group element G here. And the composition is the easiest one that you can think of in this situation. So G Z1, Z2 is composable with G Z2, Z3 and gives you G Z1, Z3. You should think of these Zs here as being kind of delimiters between the eigenvalues of G. Okay, so this is just a copy of the real line for a topologist, so I can equip this with an order. And so I can make sense of what it means for Z1 less than Z2 here. And if in that situation, I define the fiber of my Fell bundle by this construction here. And now I have to turn this into a bimodule over the algebra D. And there's a canonical right multiplication that you can use. And to get the left multiplication, what I need is, I need an identification of the endomorphism algebra of this vector space, tensor D, with D itself. And this is where I really need that I have an exponential functor, because the extra structure from this exponential functor allows me to choose this isomorphism here in an associative way. So I really get an associative product in my Fell bundle. And then if I just flip the order here, this is more or less forced on me that I have to take the opposite bimodule of the place where I have to switch the two. So this is there's no choice that you can make. You have to pick this, and this turns out to be a Fell bundle over this groupoid curly G here. Okay, so why does all of this make sense? So first of all, if I pick this determinant functor with to the nth tensor power here, then the C-star algebra that I get from our construction just turns out to be the complex numbers. And this whole construction boils down to what's the description of the basic gerbe, a la Murray and Stevenson. And this is actually this this gerbe is known to represent this classical twist that Fried, Hopkins, and Teleman used at level M. But in general, you get something more interesting, and we can compute these higher twisted K groups twisted by our Fell bundles, at least in the case where the group is just SU2, and then for all exponential functors that one can come up with. And for the group SU3, I can compute this, but only after I tensor with Q. And the only reason for that is I have to work out the differentials in a spectral sequence, and there's an easy way to get rid of them just by rationalization. Right, so what's interesting about these is that this group here, that is the analog of this Fried, Hopkins, Teleman group, that still turns out to be a ring. But it now has an extrinsic ring structure. So it's a quotient ring of the representation of a localization of the representation ring of the original group G. So, and what we would love to know, of course, is whether this sort of extrinsic ring structure really comes from something intrinsic, right? Whether there's, and in the classical case, this is related to the fact that this gerbe that you have here, that this is multiplicative. But I don't know what multiplicativity should be for this Fell bundle twist here. So the situation is even better. Sometimes what we get are indeed fusion rings. So for example, for SU2 and this exponential functor here, you get a fusion ring. Right, and I think this is everything that I wanted to say. So thank you very much.